Hi y'all, back for another round of physics. And today we're going to go at it. We're going to start looking at gravity. So specifically Newton's law of universal gravity. So let's go ahead and write that down from not last video, but I believe it was 2 videos ago. So I'll go ahead and write this down. G1 M2 over R squared R hat. Excuse me, that 2 doesn't look good. There we go. So Newton's law of gravity. And today I thought let's at least get some ideas about Newton's law of gravity and circular motion in particular. And circular motion. Circular motion. Okay. And just to give you kind of a setup on what's going on here, in the historical progression of physics, we started off with, of course, just straight out astronomy. And as we historically progressed, we moved from the Ptolemaic model, a geocentric model, into heliocentrism. And you have personalities like Copernicus and Galileo that are associated with that transition. But there's a couple of couple of astronomers. One that went by Tycho Brahe, and his protege, I think it's Johann Kepler. Now, the reason I even mention these is that Tycho Brahe did a lot of observations, a lot of measurements of the sky and the location of the planets in space with respect to the background stars. What Johann Kepler ended up doing was taking all of these numbers that Brahe had recorded over the course of probably 40 years, something like that. And he actually looked at the data and started noticing patterns. And he came up with 3 patterns that he noticed that the planets seemed to follow. Now, the story doesn't end there. The issue is that Kepler had no idea why these patterns were being followed. He knew what the patterns were, but he didn't have a good underlying model of why those patterns were being followed. And it took until Newton came along with his 3 laws to actually describe Kepler's observations. So first of all, I'll give you Kepler's laws. These are something that is nice to know. They're nice shortcuts. Kepler's laws. Number 1, planets orbit in ellipses. With sun at one focus. Okay. Number 2 is sometimes referred to as equal area in equal times. I'll have to describe what that means. But essentially, it means that if you think about a string going from the sun to a planet, and you think about the area that's swept out by that string, say in one day, it doesn't matter where in the planet's orbit you are. The area swept out by the string will be the same, regardless of where the planet is in its orbit. So sometimes that's why it's usually shortened to equal area and equal times. The third one is interesting, and the one that we'll focus on today. It says that if you know the semi-major axis of a planet, so basically the size of the orbit, and you know the period of the planet, those two are related. Namely, the radius or the semi-major axis of the orbit is equal to the period squared of the orbit. And probably more formally, I probably shouldn't write it exactly like this, so let me X that out. How I should write it is I should say the semi-major axis of a planet, and I'll put planet 1 cubed, divided by the period of that planet squared, is a constant. And we'll see where we'll use Newton's laws to kind of get an idea about where this comes from. So this is the big thing that I want to go after today. And from the historical perspective, this is really something that helps cement Newton's laws as the appropriate model for physics. He came in with his 3 laws plus gravity and said, if you take these models, then I can explain how Kepler's laws arose. So that's kind of cool. Anyway, okay, so let's get an idea here. Let's get rid of this rigmarole. And what we're going to start with. Well, let's start with this. And we're going to simplify a little bit. So in Kepler's third law talks about semi-major axes. So I guess I should probably sit down and at least draw what's going on there. So let's go ahead and draw. Let's say here's an oval. Okay. Now, a semi-major axis you can think of as being the distance, the farthest distance across in an oval. Okay. So if you think about the longest chord that you can draw from one side to another, that longest chord is called the major, is called the major axis. Axis. Of course, the smallest chord that you can draw, so you visually can kind of see the smallest distance from one point in this, how do I say it, one point to the other point. This would be called the minor axis. Minor axis. Okay. And I should say it's the smallest distance that bisects the major axis. That might be a better way of saying it. Or a third way would be this, the minor axis is always perpendicular to the major axis. So it's the smallest distance that bisects the major axis, and it also happens to be perpendicular. In any case, so what the semi-major axis is, wow, really off tonight. Sorry. The semi-major axis is the major axis. Sorry, man, just really off. Excuse me. The semi-major axis is half of the major axis. So if you identify the major axis, then half of that would be the semi-major half axis. So we're talking about this distance here. Okay, that's Kepler used the variable a to represent that. So in Kepler's third law, a represents this distance, the half distance of the major axis. Okay. Just for sake of completeness, since space is really important for the progression of physics, I should say that, for example, if this is the orbit of some object around the sun, so I'll put the sun right here, for example, this would be considered one focus of the ellipse. And when the object is the closest possible to the sun, that is called the perihelion. Perihelion. Okay. Closest to sun. The point that's the furthest away from the sun is called aphelion. Helion. Okay. Or away. Furthest away. So I usually remember A stands for away. And of course, helion, that appears in both of these words, is related to the word helios, which is also the sun. The period of the orbit is how long does it take an object starting at one location to go around and complete its orbit. Okay. So period is how long? Period. And more generally, I'll say how long to repeat. So you're dealing with something that repeats frequently, and the period would just say how long it takes between repetitions. So for example, the period of the Earth's orbit is 1 year, or the period of your birthday is 1 year. Something like the rotational period of the Earth, 24 hours. Okay, so it's something that happens with regularity, and then you can state how often it occurs. Okay, well, let's get this off the table. Okay. And what we're going to deal with is, here's the general idea. I would like to see if we can come up with some physical basis of Kepler's third law. So what we want to do is we want to apply Newton to, I'll put in quotes, prove Kepler's third law. And we'll make one assumption here. We're going to go ahead and assume, circular orbits. Circular orbits. So that's just to give you kind of some sense about what you would actually do to show this. We'll go ahead and assume circular orbits just for simplicity. Now, if you really get jazzed about it, you really want to know, come up to my office. We can always crack open what's called a mechanics textbook, and there will be the full-blown, in all of its glory, derivation for ellipses rather than circles. So we're going to simplify just for sake of time and making it a little bit easier and conceptual. So here's the deal. We have a star, namely our sun. I'll color it yellow just so that we can say, ooh, how pretty. And let's say we have a planet like Earth. Okay. And we know that this planet will travel around the sun in a nearly circular, we'll call it a circular orbit, although it looks terrible. Maybe I should have done this instead. There we go. We're going to travel around the sun in a near circular orbit. Boom. There we go. And here's the question. Here is the question. If I'm thinking about this, so my system is the Earth. It's the Earth. What's in the surroundings? It's the sun. Okay. And here we're going to exert the big gravitational force. Okay, so big G, not little g. Now, the second question I should ask you, if I'm thinking about this, I should do a free body diagram. So here's my Earth. And in this position that I've drawn, what direction is that gravitational force? It's toward the center of the sun. Remember, when we do Newton's law of gravity, this Fg, we'd have big G, m1, m2, the Earth-Sun distance right here, and then we have that negative r hat. In one of the previous videos, I said, hey, this negative r hat ensures that the gravitational force acts to pull the two objects together. So in this case, the gravitational force would be down. I shouldn't say down, I should say towards the sun. So I'll put Fg here. Now, I'll tell you that the Earth travels in its orbit counterclockwise. That in itself doesn't really matter very much for our derivation here. What is interesting, though, is if it's traveling counterclockwise, the question I have for you is, what's the angle between the gravitational force and the direction of motion? And hopefully you see that they're actually perpendicular. The direction of motion is going to be tangent to the circle, so the velocity of the Earth at this point in time, this location, will be this direction. But my gravitational force is going to be pulling downwards. Something like this. Okay. Now you have 90 degrees between your velocity and your force. So I ask you, does your speed change, your direction change, or both? The answer is your direction. Okay. So we're going to have a force that is always perpendicular to the direction of motion. And because of that, my velocity will continually change direction, but never change length. And so we'll end up with a circular pattern. So we've got our system, our surroundings, we've got our free body diagram. The next thing that let's go for is let's go and see, and what we're really after again is we want to figure out, we want to relate the period to the orbital radius. So I'll put in right here, we're interested in relating how long it takes Earth to go around, for example, to the orbital radius of the Earth. So let's go ahead now and take a look at Newton's second law. We have F net is equal to ma. Now thinking about the Earth, the only force that's acting on is this gravitational force. So I will go ahead and put F, oops, excuse me, got carried away there. I'll go ahead and put in big G, m1, m2 over r squared. Now, the other thing I should ask is we have a circular motion. And because we have circular motion, we have an expression for the acceleration. And that and please bear in mind, this is a definition, and this is a definition that comes from math, from a geometric or a math argument. If you don't remember that, I'll put a reference back to the previous video just so you remember which one we're dealing with here. But we had a geometric derivation and also, I believe, a calculus derivation for the acceleration when an object moves in a circle. Excuse me. Okay. We found that if an object is moving in a circle, then the magnitude of the acceleration can be expressed as the speed of the object squared divided by the radius of the circle. And in fact, with that calculus derivation, we went even further. We said, hey, this acceleration has a magnitude of v squared over r, and it's directed in the negative r hat direction. So let's go ahead and use this. We're going to use that right here for this acceleration. So we have this relationship, negative r hat equals the mass of the, and let's be careful here, this should be the mass of my system, so I'll put Earth. I'll put Earth here for one of my masses. We'll call this one the Sun. It's a really ugly S, but let's go ahead and do that. So you have the mass of the Earth times v squared over r in the negative r hat direction. You say, oh, goody, goody. Negative r hat, negative r hat. Should make some sense. The acceleration should be in the same direction as the net force. If the net force is towards the center of the circle, then the acceleration better darn well be towards the center of the circle. So physics has worked out for us so far. Sorry. Physics has worked out for us so far. So let's keep going. The next one, oh goody goody, I missed that one. We also see that the mass of the Earth actually cancels out. Mass of the Earth here cancels out the mass of the Earth there, which is also a convenient little thing. It doesn't matter if we're dealing with the Earth, or we could have been dealing with Jupiter or Saturn or any other planet. It does not matter. So I'll go ahead and write this down now. I'll say G m sun over r squared equals v squared over r. And here, the next piece I want to ask you about, okay? Can I relate the distance traveled, the period, and the velocity? You say, yeah. Okay, the velocity of the Earth. So let's go ahead. I'm going to get rid of this here. Let's go ahead and clear this off. So coming up here to the top. So we say, yeah, I can relate the speed of the Earth to the radius and the period. Say the speed of the Earth is simply the circumference of the circle divided by the period. The circumference of the circle being the distance traveled, the period being how long. So I've got a speed, total distance divided by time. Let's go ahead and substitute that into the expression that I have here. And so we end up with something that says G mass of the sun over r squared equals parenthesis 2 pi r over the period p squared times 1 over r. Of course we see, oh yes, we've got some more cancellation. We can cancel that and we can cancel that. So we get rid of those. And what I'm going to do is I'm going to group all of the constants on the left side of the equation and all of the variables on the right side. So what I'm thinking of here is G, the gravitational constant, the center mass, 2 and pi. I'm going to shift those over. So I end up with G m sun over 4 pi squared. Hang on a second. So I've moved those over. Now the right side of this equation, I have r squared with another r. So I have r cubed. And I have p squared. P squared. Now let's go ahead and sit back and take a look at this equation for a second. What we're saying is, okay, if we know the radius of the orbit, it's giving us a relationship between the cube of the radius and the square of the period. Note everything over here is just a constant. 4 pi squared constant, g is a constant. The mass of the sun, that's basically a constant. So it's giving us a relationship. I should point out that if you notice, this will apply for any of the planets because all the planets revolve around the sun. And so that comes back to Kepler's third law. Kepler's third law told us, hey, the cube of the orbital radius, semi-major axis, and the square of the period is a constant. And here's the constant that it's actually equal to, gms over 4 pi squared. What does this mean? Let's go ahead and give you an example. Give you an idea about this. So, keeping in mind that r cubed over period squared is equal to a constant, let's go ahead and give you a couple problems. Say you're Kepler. Okay? Say you're back in Kepler's time. And the thing that's, the first question I should ask you is when you're looking out at the sky and you're looking at the planets as they move through the heavens, one of the questions I should ask is, which thing is easier for you to measure? Is it easier for you to measure the period of a planet, or is it the distance that the planet travels? You say, hey, I've got this. It's the period. That's the thing that's easier. You have to sit outside. You have to be a bit patient, but you sit outside night after night after night, and you look at the sky, and then you figure out, okay, Venus is there. And then you just sit there and watch and wait until Venus gets back to the same location in the night sky. Okay? And if I told you this, let's say Venus, the period of Venus is 0.62 years. Okay? The question I have for you is, can you figure out the orbital radius of Venus? So I'll say, what is the orbital radius of Venus? So go ahead, pause the video for a second. I'll let you take a shot at it. Good. Here we go. Well, I know that r cubed over p squared is a constant, so I could go at this one of two ways. The first way I could go at it is I could say, well, I've got this equation, r cubed over p squared equals g, the mass of the sun, over 4 pi squared. And you could hammer away at it, right? You have r cubed equals, well, g is 6.67 times 10 to the negative 11th. Okay. Gravitational constant. The mass of the sun is something like 2 times 10 to the 30th kilograms. We have 4 pi squared. And then we have the orbital period, 0.62 years. Of course, then I have to convert years to seconds. So there's 365 days in a year, 24 hours in a day, and 3,600 seconds. Oh, and let's not forget, that would be the period. I better square that sucker. Okay. Now you can go through and hack that out. You've got all the numbers. You just take a cubed root at the end of the day. Take a cubed root at the end of the day. And boom, there's your answer. And I encourage you, go ahead and do that. Just double check to make sure I'm not, pulling some fast one on you. But there's an easier way. Let's go ahead and take a look. What's the easier way? Well, the easier way, or the faster way, is to recognize again this right side as a constant. So a different way to go at this would be, hey, let me compare planet 1 to planet 2, R2. over r period 2 squared. That's what, if this applies for any planet orbiting the sun. Actually, I should go even further. It applies to any object orbiting the sun. Could be a planet, could be a satellite, could be an asteroid, a comet, does not matter. This applies to any object orbiting the sun. So here we go. Now the question is what's an object that orbits the sun that's going to be really easy to do this calculation with? And I'll say, let's use the Earth. Not a bad idea. So here's what we're going to do. We have the radius of Venus, which we don't know, cubed. The period of Venus is 0.62 years squared. Okay. The orbital radius of the Earth, we'll call it, and here's the sneaky part, 1. Okay. Say, whoa, what do you mean we're going to call it 1? Well, historically, that was the hard part. One of the hard problems in astronomy was measuring the Earth-Sun distance. So what astronomers did was they came up with a new unit. They said, we will call one astronomical unit is the Earth-Sun distance. Earth-Sun distance. And taking the Earth-Sun distance to be one astronomical unit, Kepler's third law allowed astronomers to determine the distances to all the other planets, okay, in terms of the Earth-Sun distance. So on our final answer here, even though these are weird non-SI units, our final answer will tell us what percentage of the Earth-Sun distance is Venus away from the sun. Okay. So let's do that. And of course, the nice thing about that, 1 cubed is still 1. And in the denominator, we'll have 1 year squared. Now we just run it, right? You can do all the calculations, yada, yada, yada. So you should get something like the orbital radius of Venus is equal to 0.72 astronomical units. In other words, Venus is 70% of the Earth-Sun distance, right? 70% of the Earth-Sun distance. Now, of course, this is pretty easy. You don't have to do any different calculations or unit conversions or anything. You just do the straight ratio and boom, you've got it. So that's another really cool thing. Now, I will have some warnings for you when you're applying Kepler's third law. There's a couple of things to be careful about. Well, actually, essentially one. Okay, if you want to, well, two. If you want to actually apply Kepler's law in this form, so you want to do the calculation of the constant, then you need to make sure that you're in SI units. Okay. Please remember that the gravitational constant, 6.67 times 10 to the negative 11th kilogram meters squared per, oh, excuse me, got my units mixed up here, Newton meter squared per kilogram squared. If you want to use this value for the gravitational constant, you have to make sure that you're in SI units. So that's the first one. The second one that I want to point out is if you decide that you're going to use this kind of form for Kepler's second or third law, if you want to use this for Kepler's third law, please, 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 please make sure you are comparing two objects that are going around the same central object. And what I mean by that is you have to make sure whatever you're plugging in on this side of the equation, it has to orbit the same thing that the object in this side of the equation is. Okay. So you notice, for example, I did Venus and the Earth. Those are both orbiting the sun. I cannot do something like Venus and the moon. Okay, if I use the moon over here, that doesn't work because the moon orbits the Earth. Venus orbits the sun, the moon orbits the Earth. I can't do Kepler's third law to compare the two. Now, if I wanted to do something like the International Space Station, then indeed I could use Kepler's third law and compare that with the moon. Okay? Because those both orbit Earth. The only difference that would be is if I decided to do this comparison, ISS and the moon, if I wanted to actually do the calculation out, I would replace the mass of the sun with the mass of the Earth. Right? This mass is whatever that central body is. Okay? So that's one of the nice things about Kepler's third law. And also, it's a nice application of circular motion for using circular motion, so that centripetal acceleration. Centripetal acceleration. And I'll write this down, this v squared over r idea. Okay. That's just a brief video, just historical context. The next video, I think we'll sit down and we'll do a couple problems with circular motion and just kind of ramp up the difficulty a little bit. Thanks for your attention. I'll see you next time.